Hi guys, in today's video we'll be looking at another example of an extended body in equilibrium. So the concepts here will be very similar to last video. Basically we'll have the same two conditions that we're concerned with, which is to say if it's an equilibrium, that means that the sum of the forces, so the linear acceleration, must be equal to 0. And similarly, the sum of the torques about any point must be equal to 0. So again, if we remember last problem, we sort of struggled a little bit with trying to choose our pivot point. And so this will be a problem that comes up again today, is sort of what is the most direct pivot point to choose. Of course, any pivot point we choose is going to be equally valid, but certain pivot points will give us our information more directly. So we recall sort of one thing to always keep in mind is that whatever pivot point we choose, any forces acting at that pivot point will not give us any torque. And so our resulting expression that we get from this sum of torque equals 0 will not include that force. So sometimes that can be very useful to us. So otherwise, we will just go ahead and start, and we'll do this in very much the same way. We'll look at the free body diagram, we'll impose these conditions, and then we'll get to a solution. Okay, so the problem statement for today reads as follows. One end of a uniform meter stick is placed against a vertical wall. The other end is held by a light weight cord that makes an angle theta with the stick. The coefficient of static friction between the end of the meter stick and the wall is 0.4. What is the maximum value the angle theta can have if the stick is to remain in equilibrium? At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out up here. So it's pretty simple. We have a meter stick, and then we have a string which is tied at some angle theta. So all we're given here is that mu_s is 0.4. So the first thing we want to do is we want to think about what is this problem really asking us for. So it says it wants us to find the maximum angle theta such that this meter stick is still in equilibrium. So whenever we have these sort of maximum problems, oftentimes there'll be some friction force involved. And so in this case, we see that amounts to, we have a static friction force between the wall and the meter stick, which we know is always going to be less than or equal to mu_s times our normal force. So really this is going to amount to, we want the maximum theta. So really we're looking for our angle theta such that our force of static friction is at its maximum. Because anything larger than that would mean that this meter stick will be slipping along the wall and we're not in equilibrium anymore. So really this also amounts to, we want a maximum static friction. So that is when static friction force is equal to mu_s times our normal force. So really what we're going to do today is just impose the fact that we want our static friction force to be its maximum, which means it's equal to mu_s times normal. So first step in these kinds of problems, once we decide what it asks for, is to draw our free body diagram. So I'll do that down here. And so we have our meter stick right here. And then we are given, basically there's really only two forces acting that we see here. There's actually more on the other edge, but for now let's start. We have our force of tension acting up and to the left here. We know we have a weight force from the meter stick, which will act at the center of mass. And then here at this point of contact between the wall, we have a couple of forces that might be a little bit trickier to solve for. But we first of all see, of course, this is not slipping down, so there must be some friction force here, which will be applied upwards to keep this from falling. And there's actually going to be a normal force from the wall as well, pushing out on this meter stick. So this is something that's easy to forget, so let's make sure when we do these problems we recall there's also a normal force acting along from the wall, pushing this meter stick so it doesn't go through the wall. And so one way to see that, and what I always like to do with these problems, is sort of to, once I draw my free body diagram, if we know it's in equilibrium, I like to make sure that in the x direction and the y direction, we have pairs of forces that could feasibly cancel out. Right? So if we had forgotten this normal force in the first place, then we could have looked at this and seen that the tension force has a component in the negative x direction. And so we know we need some force to cancel that out. So this is at rest in the x direction. And so in this case, that turns out to be the normal force. But without that, of course, there is an unbalanced force pushing to the left, and this would accelerate to the left. So that's a good way to it's a good thing to do as soon as you draw your free body diagrams to make sure you have all of your forces in there. And so now, of course, we can just proceed as before, which is to say we want to impose that the sum of the forces should be equal to 0. And this is true in the x and in the y direction. So we'll start with x, and in our x direction, we see we really have the force, the normal force, and I'm also going to break up this tension force into its components. So we have, of course, a tension force component in the x. So this is it's tension in the x. And then it's got a component here in the y, so tension y. And again, we've done this a bunch of times, but we see now we have a triangle, so we can do our trig to solve for those quantities. So for our x equation, we see we have our normal force pointing to the right. So this will say F normal is our positive force. And then we want to subtract off the tension force, only the x component, of course. So in this case, I'm going to sort of just do the trig in my head. So we see this tension x should just be equal to t cosine of theta. So this is just t cosine of theta. And then all of this should be equal to 0. So we can go ahead and sort of solve, and we actually get a nice little equation where we really just say the normal force is equal directly to t cosine of theta. So this will come in handy. But let's go ahead and move on. I mean, we still don't know the normal, the tension, or the theta, so clearly that's only one equation and 3 unknowns. So in the y direction, we'll do the same kind of thing. The tension force up is going to be our positive direction, so we have tension in the y, static friction, and then a weight force. So in this case, we have t sine theta is t in the y, and then we want to add to that our force of static friction. And we see over here, we know that the force of static friction should have the form mu s times normal. So I'm going to go ahead and plug that right in. So this should be mu s times normal force. It's just the force of static friction. And then we want to subtract off our weight force. So this should also be here in blue. And this will just be minus weight of the stick. And all of that should be equal to 0. So here we see we have one equation. Again, we have many unknowns. So at this point, we still can't solve our system of equations. We still have more unknowns than equations. But what I'm going to do instead is I'm going to simplify this equation here, which is to say we have a direct relation for the normal force. So I'm just going to go ahead and plug that in down here. And this is just a little bit of algebra, which will help us out. So everything else will remain the same. We'll have t sine theta won't change. But now the friction force will become plus mu s. And this normal force, I'm just going to plug in what we solved for before, which is to say t cosine theta. So this right here got plugged in. And then I am just going to also move this weight force over. So all of this should be equal to the weight force of our stick. So here now is a relation we see. We still have many unknowns. We don't know the tension, we don't know theta, and we don't know the weight. So we still have one equation really here and 3 unknowns. So we're going to have to keep going. But we do know, of course, that we have the sum of the torques about any point we choose is equal to 0. So of course we could choose a couple of different points, and we at some point should be able to algebraically solve and probably get to our desired theta. And so in this case, what I'm going to do is I'm going to choose one pivot point, and that pivot point will be this left edge of the meter stick. So my thought process here is just, we see we have 2 forces that we don't know too much about. We have the normal force and the static friction force. So if we choose the pivot point here, our resulting relationship will not depend on these 2 forces. So once we choose this pivot point, we can impose the sum of the torques here. And we see then we are going to have the weight of the stick will give us a torque which is going to try to rotate this meter stick in the clockwise direction. And the tension force will try to rotate the meter stick in the counterclockwise direction. So those will oppose each other, and we can basically set these equal and opposite. So the sum of the torques, I'll do this right here, our sum of our torques here is just equal to torque from the weight of the stick plus, and so let's go ahead and say that clockwise is going to be our positive direction. So then this will subtract from the magnitude of our torque from our tension force. That should be equal to 0. So these here are magnitudes. So basically all I'm doing is I'm saying whatever the size of the torque from the tension is, it should be equal and opposite to the size of the torque from the stick weight. And so in this case, that amounts to setting equal torque from the weight of the stick equal to the torque from the tension. And similarly, we know that torque is equal to R times F perpendicular. So here for our weight, of course, that's pretty straightforward. That just means the torque here is going to be our distance from our pivot point. So for the stick, that's 0.5 because it's halfway to the end of the stick. And then the torque is going to be R times F. So that is just, this is our R. So this is just multiplied by our weight. Right here, this is just our torque, our R times our F. Similarly for our tension force, again, we only want the perpendicular component. So we're only going to take the tension force, the Y component of that tension force. But otherwise it's the same. Radius is 1. And then the force is going to be Ty, which will be equal to T times sine of theta. So, blue. Okay, so we now have another relation, and right away we can actually see we can solve this for the weight of the stick. So I'm going to go ahead and do that. Basically just rearrange this to say the weight of the stick we see here should be equal to 2t sine theta. All I'm doing is multiplying over this 1/2. So we have a relation for weight, and so yet again, I'm just going to go ahead and plug that straight into this relation we have up here. And once we do that, with a little bit of algebra, we can get to the step, and again, follow along in your solutions at home, but plugging this into here gives us that, in fact, let me start here, gives us that our tension sine theta should be equal to our mu s times t times cosine of theta. So here we now have one relation, and we see we have two unknowns. We don't know t and we don't know theta, but we do see also that the tension force is in both equations. So what we can do at this moment, instead of having to imply this torque about any other pivot point, we can just see that our tension force is going to cancel out. Basically, we'll divide this equation by t. These two t's cancel. And we now get our relation that's tangent of theta. And so again, follow along for this trig at home, but basically divide by the cosine, and we'll get tangent of theta is equal to mu s. And so at this point, we know mu s. That's the only thing we know. And we can solve for this directly by just taking the inverse tangent of mu s. And so what we do when we do that is we get a solution that our maximum angle theta should be equal to 22 degrees. So that's to say, anything, if the theta is larger than 22 degrees, we're going to have a problem, and this won't be in equilibrium. It'll start slipping down the wall. Okay, so let's recap what we've done. We first drew our free body diagram, and then set the sum of the forces equal to 0 in x and y. We chose the pivot point as the left edge of the bar, and set the sum of torques about that pivot equal to 0. These equations allowed us to solve mathematically for the required angle. Okay, so I hope this problem was helpful to you, and I hope you have sort of some better understanding of how to approach these problems and how to approach the algebra involved. So if you have any comments on this video or any of the videos, please post those to the right. There should be a comments link. Thanks for watching.